Good morning, ladies and gentlemen. May peace be upon us all. Welcome to the Honorable Associate Professor Roil, Doctor of Philosophy, as our guest speaker. Honorable Mr. Luhur Akbar, Bachelor of Engineering, Master of Engineering, Doctor of Philosophy, as moderator. Honorable Mr. Anggadeta Sirajuddin Aji, Bachelor of Science, Master of Science, as the lecturer of the course. And dear friends of the environmental engineering students at Brawijaya University. Good morning and welcome to today's guest lecture on wastewater treatment, organized by the Environmental Engineering Study Program of Brawijaya University. We are truly honored to have your presence here, and we hope this event brings valuable insight and knowledge to all of us, especially in environmental engineering. I am Chiara and I am honored to be your Master of Ceremonies for this morning's event. First of all, let us give thanks to God Almighty for His blessings, so we are able to gather here in good health and spirit. On behalf of the committee, we would like to express our warmest welcome and appreciation to all of you for being here, especially to our honorable guest speaker, Dr. Roil, who has kindly joined us today to share valuable insights on biotechnologies in wastewater treatment. To begin this event in good spirit, let us take a moment of silence to pray according to our respective faiths and beliefs. You may pray in your own way during this brief moment. Let us pray together. Thank you. May this event be blessed with wisdom and fruitful discussion. Allow me to briefly outline today's agenda. First, we will begin with a welcoming speech. After that, will be followed by the main session, a guest lecture presentation on wastewater treatment. After the presentation, we will proceed to an interactive discussion and Q&A session where you can engage directly with our guest speaker. Then we will capture this memorable occasion with a group photo. We will conclude with some closing remarks. With that, let's proceed to our first segment. We will move on to the main agenda, the guest lecture on wastewater treatment, with the theme Biotechnologies in Wastewater Treatment. In today's gathering, we are honored to have Associate Professor Roil, Doctor of Philosophy, Esteemed Associate Professor at Brunei Darussalam University, who will share his expertise with us. For this session, I would like to hand over to our moderator, Mr. Luhur Akbar, Bachelor of Engineering, Master of Engineering, Doctor of Philosophy, who will guide us through the presentation and discussion. Before entering today's main program, allow me to first address our moderator. Alright, since our moderator is ready, Mr. Luhur, the time is yours.
Thank you for the Master Ceremony for the introduction. Assalamualaikum warahmatullahi wabarakatuh. In this opportunity in the program, we will have a lecture from Associate Professor Dr. Roil. This is the second series, I think, and the topic will about the biotechnology in the wastewater and wastewater treatment. And for the session, I think we will divide into two parts. The first one is about the lecture, I think for around 60 minutes, and the rest will be discussion. I think the time is yours.
be better at it. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to thank you all to come here today. I know it's a series of long holidays, but no worry, you will have no class on Wednesday, so you can skip class on Tuesday and then have 4 days, 4 days break. Okay. Yeah, because I fly here last night and then tomorrow I will return, so it's a quick trip. So I want to continue what I left last time. Okay. So today's focus will be more on biotechnologies. I think for the second year student, this is a little bit too advanced. It's okay. You know, you just try to understand. Maybe once upon a time in the future, you will recall back this moment. Okay, this is what I learned in the university. I finally understand. And a lot of that thing happened to me as well. Sometimes it takes 10 years, 15 years to really understand what does that mean. Okay, so it's okay. You try your best. I'll give you the handout later on. Actually, my handout is ready, but I didn't know how to pass it to you. So I divide my lecture into 4. So first of all, I want to offer to you about the design strategy. Okay. So when I have, normally as an engineer, you don't have like, you have a problem. I have this wastewater. Okay, how could I treat it? Okay, the thing is, shall I do everything, or shall I do the bare minimum? So what is the strategy? That's number 1. And the second one, I will touch a bit on membrane bioreactors. Okay. Then biological nutrient removals, and finally a little bit comment on resource recovery. Yeah. So first, we don't most common treatment process is the activated sludge, domestic wastewater, industrial wastewater, because most of those water contains organics. Okay, what happened in biological process is we oxidize biologically organics into stable product, into the solid, into water, into CO2. Okay, but well, not all of the wastewater necessarily be treated with that process. Okay, we have to look into what will be the capacity, what are the pollutants, what are the pollutant concentration. Okay, you might need to question. I will refer that in the end. You might be asked question. Shall I call this a waste? Okay. Okay. That's hello. Okay. Now it's better. Okay. I don't have to speak loudly. Yeah. So you're given the things. People tell you that okay, you're going to treat this wastewater. Okay. One thing you should ask first is that correctly assigned? I mean, is it really wastewater? For example, okay, I have a water containing sugar and water, just sugar and water. Well, if this is coming from a process, you tell that is a waste. Okay, it's a waste, but you don't use it. But then you should see it now. Now it's up to you as an engineer. Okay, you look into that stream of flow and then ask yourself, shall I call this waste or a resources? Because water is resources as well. Okay, and then if it is a waste, for example, what will be the goal? What will be the final quality I want? Then from that you find out what is the treatment. Okay, it's like a doctor. Okay, you diagnose the problem, you know what is healthy means. Okay, and you don't treat everything. Okay, you don't give all medicine to people. They might die. You have to be very specific. This is exactly what we do in treating wastewater. Okay, so if it's contained, for example, the waste contains a lot of metals. So maybe you just do the simple aeration, oxidize the metals, okay, and settle it down. So it has to be treatment for purpose, not just all for everything. Okay, okay. For example, you have a flow parameters. The parameters define the flow, define the size, how big it is. Okay, and then you have to think as well for this volume. Shall I do it a multiple unit in parallel, or I just do one very big? Okay. Okay, you can, for example, I can camp all of you in one room in a dorm, or I can give all of you one room. Okay, all of you will sleep, for example. That's the logic. Because this one. And then it is content organics, how high it is. If it's too low, okay, if it's too low, there might be no treatment. For example, okay. The standard BOD, let's say biological oxygen demand, I hope remember what we learned previously. Let's say the standard for discharge in Indonesia is around 50, okay? And then you have a waste stream that contains 60, so it's 10 grams. Still it doesn't meet the requirement. What's the easiest solution to lower the concentration? What is the easiest solution? I got a 50 as the target. My influence has a 60. Very close. I mean, this is a small thing. So, anyone? Voucher OFO, 50,000. Anyone? What should you do to lower the concentration? Okay, the challenge stop. You have, okay, or a coffee is too sweet. To make it less sweet, huh?
Add water. Add more water.
You add water, yeah, you dilute it. Okay, easiest way is to dilute it. Okay, but that's the thing. So can I just dilute it, or shall I treat the waste? Okay, that's another consideration. And then we have is there any solid? If there are any solid, what way to separate the solid? There are many ways that you can look into the technologies to separate solids. Easiest way is settling, if it can, but you will need a very huge unit. Maybe the fastest way is to filter, but then you have to do investment, blah blah. So when you do engineering, it's all about, in the end, is UUD. It's all about money. You punya duit. It's just all about money in the end. And then you got other factors. So all of this you consider. So it's not just like, okay, I have waste, no, I have solution, bang. So it's you are a doctor, but you don't treat human. You treat water, sick water, or polluted water. So your job is to make the water healthy for us to consume. So no, you come to a doctor, you get diagnosed influenza, and then you don't give all kind of medicine, right? Just give it, just enough medicine to cure whatever diseases. Okay, and then sometimes, what will be the goal? On the left, this one is the limit normally requirement for the municipal wastewater. If you can achieve this, well, this is not a treated water anymore. This one can be reused. So you can, instead of discharging the water to the body, you can reuse the water. Okay, if you meet this quality. So those things. So the thing is that, okay, to reuse the process, I need an extra effort. The extra effort require investment, require money. But then in return, I will get the water to be reused. So you balance between the two, whether it is more economical to just discharge or to be reused. So it's quite fun actually if you really go into it. Okay? Okay, next. So next, I will move on to the. So those are the engineering consideration. I think one of the participants last time asked how to select the things. The units you can read it, but the way the thinking process you got to learn in school. And next, I will move on to another process. It's called membrane bioreactor. Okay. So I will go through it slowly later on, but I want to remind you how can we treat wastewater containing organics? Okay, so wastewater containing organics, although the organics is small, it's changed the name. You know, I think water is one of the substances that treated unfairly. Why? Have you drank tea?
Yes.
No, it's not tea, it's water. Well, the component of a tea in a tea is probably 0.01%. The tea itself, the 99.9 is water. But why you call it tea? Okay, and then you drink coffee, right? This coffee is just a teaspoon, a coffee spoon, very small, and then in a glass of water, hot water. And yet we say it's not water, it's a tea. The same thing, wastewater contains a very minor component of organics. Yet the water now has to give up and we tell it's waste. So wastewater is actually water, majority is water, containing organics. And then what we do is we oxidize it with the help of biological agent, in this case is cell, to produce more cells, generate CO2 and some of the cell metabolites. This is how I simplify the aerobic process. So this is the thing, microorganism eating the things. This is the cell need the oxygen, and then the pollutants is considered as the food. So this is a natural process that happened. We learned this one last time. So an engineer look into what happened in the process and try to design something. Can we use this natural phenomena? Okay, put a little bit of engineering in it and use it for our. Check my time. Too slow. And use it for our benefit. So what we do is, so we create a chamber here where we grow a lot of this cell, okay, which is the secondary effluent things. This is bioreactor where it's consumed the pollutants, and then we produce the treated water and we produce solid disposal. So this is what we do in engineering. So this process called activated sludge. Okay, this is the simple layout of the process. Activated sludge. You have two steps: biodegradation and then separation. Okay, you separate the cell that you produce. Any excess, this is waste, activated sludge. We throw it away. So actually, your wastewater in the end become metabolites that actually it is in solid. So what happened to the solid? We dump it, landfill, we burn it, incineration. So all of the organics that is in water, although in the small quantity, but if you have a huge volume of water, in the end you will have a plenty number of solid here. The solid we send to the solid treatment plant. Okay? The problem here is a classic. Okay? The key, the bottleneck of the process is on this part. So, how if the water doesn't want to separate? Sorry, how if the cell doesn't want to separate? So when the cell doesn't want to separate, it's carried away to the effluent and it's ruined everything. Okay, it's ruined everything. What they call as sludge bulking. Sludge is supposed to be slim, but when they got angry, they become very bulky. Okay, they used to flop. Now, okay, in this room, you probably used to flop. Immediately, if I start to increase the temperature, you move something like that. So a lot of things can piss off the cell and then disturb its balance. For example, you put less food. Okay, they will fight for the food. They will disengage from the floor. Okay, you have salt. It's too high salt concentration. There is no water. There is no nitrogen. There is no nutrients. Okay, so in that case, if you have in unstable condition, you will have a problem called bulking. You see here, two good sludge and bad sludge. Bad sludge, after some time, they don't settle. Okay, basically they don't settle. good sludge settle, so you can treat, you can discharge this one, you can return this part here. Okay, so that's the problem. That make operating wastewater is like handling a princess or prince. You have to guard it very well. You have to really count the concentration of oxygen more than we control ourselves. Who among you that check your sugar level every day? Nothing. When we handle the activated sludge, we got to check 3 times this. Do we need to do some intervention? We need to do a lot of pre-treatments in order to stabilize the process. Okay, so the people like me, we work on membrane and say, I can solve this problem. And the way to do it is that what we call as membrane bioreactor. I will go back to that one. So it includes membrane separation. Basically, we don't settle the sludge, we separate it using a filter. That way, we can produce high quality of permeate, we can retain the biomass, we can basically increase the biomass concentration, and then while we still perform the biodegradation. Okay, that's the idea. Okay, if this is the activated sludge in more complex setup, the MBR is like this. We call it membrane bioreactor. So if you look into this, okay, this is the secondary clarifier that you saw here, but now with things called membrane. So you filter it. We don't separate the cell by simple settling. We do filtration. Now I have no problem with sludge filter. Okay, you introduce that one. You can introduce it inside. We call it submerged system. We can introduce it outside. We call it side stream. And then we can introduce it with an extra air lift, extra air. We call it a side stream air lift system. Okay, so what will be the advantage? First is superior effluent quality. Okay. Why the long explanation for this one? Okay, but one way to explain it is that now I'm not, the bottleneck is no longer the settling. So I can increase the concentration of the biomass, the cell. So imagine, if you have the same volume of the food and then now you have more people. No leftover, right? Because everyone wants to eat. So it's allow us to have this. It's quite stable. We don't have issue with bulking. And then the footprint is smaller. Okay, footprint is smaller, is like same number, same volume of the biomass, but okay, same room, but now we have more students here to eat, so you can degrade more organics. And then now we have to have mentality that it is, if I have the superior effluent quality, I can reuse the effluent instead of discharging. Okay, you look, now you invest on one unit by putting the membranes for the separation, but in another hand, I produce superior effluent quality with the stability so that I can reuse the effluent. Okay, a lot. This is I already explained to you in terms of engineering, smaller footprint. Okay, no clarifier. Okay, we can upgrade the current process. So basically, it's the same process. The second one is just you replace the membrane. Reduce excess sludge. How to explain this? Okay, when I'll explain. Okay, see, let's say the same number of cells. Okay. Okay, imagine the two things. Imagine the two reactors. Okay, one is with a higher concentration of cell, one with less concentration of cell. So, for the system with high concentration of cell, they have less food, right? Per microorganism. F food to microorganism is lower because we have to split it to more. So what happened then? So you only have enough food, you cannot reproduce, basically. not enough to have more. Okay, while when you feed it with high concentration, I mean less concentration of biomass, more food, so you have excess food. What happens if you give a lot of food to people free? They reproduce. They will produce more biomass. They will produce more cells. That is why in India we have less sludge. And for your information, the highest component in wastewater treatment, there are two. Number one is the aeration to supply oxygen. Number two is actually to treat the waste, the excess sludge. Okay, the waste, the concentrated waste, you have to dry it. Okay, you have to send it to. No, just drying is already consume a lot of money. It offer water reclamation, plant operation is simple, no issue of bulking. I explained earlier. Okay, MDR will be the future of wastewater. I think the only reason why there are activities like system available because of, well, if I'm broken, don't fix it. You know that thing, English term? If something doesn't break, why do you need to fix? You're crazy. Your car is still good. Why you need to replace? So the same thing. So you already have one wastewater treatment plant in Surabaya, in Malang. Okay, it's working. Although the MDR work, but yes, I do have. So we don't FOMO here. Fear of missing out, yeah, is it correct? No FOMO in technologies. As far if I'm broken, don't fix it. Very simple. Okay. Why you see this? Okay, in a new plan is because of stringent regulation. Okay, countries want the environment to be safer, less polluted. Then high demand of water reclamation, especially in industry. Okay, in some of industry the water cost is so high. Okay, so why don't we just reuse? It's quite logical. Limited space, health protection. Okay, the good thing about MBR is that we don't have to disinfect the discharge because the membrane will separate all of the cells, biomass including virus. That's a good thing I missed previously. And then it can work with challenging industrial. This is quite a bit difficult to explain the last one. The fact is like this one. So if you have a barrier on the secondary clarifier, so all kind of cell can stay in your system, and some cell need a longer retention time. I don't know if you can understand this one. Some cells grow very slow. So if you just waste the thing before it grows, the concentration in the system is very, very low. Okay, when you have influenza, coughing, batuk, you know the solution is that you got to drink a lot, right? Because you want to drain all of these viruses. Okay, that is retention time. We want to add retention time as short as possible. The way to do it is just by drinking. Okay, so the opposite of that is that if I don't drink, the viruses will stay in my body. Well, that's what happened in MDR. Because of you have the membrane barrier, all kind of cell can stay, and this cell might be required to degrade pharmaceuticals, some of the persistent chemicals. Okay, next features. This is the difference between the two. Okay. By the way, this is the membrane, how membrane look like. Here you see the quality in terms of suspended solid, chemical oxygen demand, total nitrogen, total phosphorus. Remember the TSS, COD I explained earlier. So it's always lower, which actually this one is like it's already meet the European Union banting water quality. Basically, the effluent of MBR you can shower with it already. The quality is so good, it meets its European Union normally very strict. Okay, this is some of the illustration about how can we reduce the footprint, the area required. Okay, So if this is the conventional activity sludge system, this area is not required. So it reduced the footprint by about 1/3. So you need a smaller area. We'll be discussing about how much is the price of land in Malang. So yeah, if the site plan is expensive, use India because it has a smaller footprint. It can reduce footprint by 33%. Okay, next. How can we do it for reclamation in industry? Okay, this is what happens if you aim for reclamation when you use activated sludge system. Aeration tank, got it. Clarifier, got it. And then this is the effluent. So in order to reuse the effluent, you need to have a few more units. Okay. For example, here you have microfiltration, ultrafiltration. This is a membrane process. Okay. And then followed by reverse osmosis. Okay. Or you can have sand filter followed by reverse osmosis. Okay. But if you do MBR, you can directly you can either directly use the effluent depending on the purpose. Okay? Because water in industry, you have a different grade. Okay? You have a different grade, and then we supply it according to the need. For example, if you want to do it for a boiler, it has to meet the boiler criteria, and that's probably different than for washing. Okay? Processed water must be very pure. Okay? That is why here you can either directly use it or do the treatment using reverse osmosis. Okay? Anyone know reverse osmosis? Okay. Not only it's famous to desalinate water. It can separate salt from the seawater. And then actually almost all of the water in Saudi Arabia, Middle East, produced through the reverse osmosis. Okay, in terms of capex is capital expenditure, is investment cost. OPEX is operational expenditure, this is the operating cost. You see here the cost. This is in Chinese yuan. Okay. RMB now is quite competitive with activity sludge process. Okay, and then here you see here this is the breakdown of the cost for municipal wastewater, and this is the operating cost for municipal wastewater. So here for industrial wastewater, the capex is higher, about 30%. The OPEX consumed mainly from energy. Okay. And then the larger you have the plant, the smaller the capex and OPEX. Okay. The larger the plant. It's quite normal. Okay. These are the summary if you want to know. Okay. So capex. Okay, this is expensive information because it's not the value, but it helps you to guess. And let's say I have this volume to treat, how much investment you need. Easy. Conventional activated sludge process, the cost is around 380 per cubic meter per day. Okay, this is the cost. MBR is around 600, so it's close to double. OPEX is very small. Okay, so this one is around 0.1 USD, so it's now about 1,700. Okay, 1,700 per cubic meter. So if people ask you how much cost to treat wastewater, that's the answer. You ask how much volume you want, and then you can have a prediction. Okay, more or less. Of course, there's a factor of size. The bigger the size, the cheaper it is. But this number will give you quite a small number, quite an accurate number. But MBR is getting more efficient. And then there is a video. You see here, the problem with MBR is that when you filter the sludge, your filter is clogged. Okay, it's blocked the pore. So you have to clean it all the time. So that is the cost factor. And then this cost factor, they produce a lot of good stuff. Like this is called lead MBR. So high volume of air pumped into the thing, shake it all the time. There is another one. So they put it like horizontally, so when you blow the air, it's like vibrating all the time. They have a rotary system like that. So when it's rotate, it's clean. And this is a filtration driven by a gravity. My life is started by this problem. So my research, okay, I introduce myself. My research is on membrane. The membrane, the things that you place on the clarifier to filter the sludge. My PhD is on that. And there are a lot of ways to do the cleaning of the membranes. One way I'm developing during my PhD, like 15 years ago, or one year. So it's by vibrating. If you vibrating the models, then it will be less clogging. The one that you saw, a lot of innovation. You can blow air, so it's shaking the filter. You can rotate the things. There are many ways of doing it. So next is designing. Last time I think sent you Excel files. Have anyone tried the Excel files?
I haven't said.
Oh, you haven't sent. But I will show you later on. So you can use that as a way to play. Okay, you play with the simulation. Okay, so these are the part that is important in designing the integrated sludge. Okay, what we need to know is the organic load. Here is food to microorganism ratio, biomass quantity and age. Quantity means the concentration, age means retention time. Okay, how much you will return? This called RIS is return activated sludge. WAS is waste activated sludge. Okay. Next issues is how good is the settling. Okay, if it settles slowly, you need a large clarifier. Okay, and then it's called sludge blanket depth. Well, what is that? So, if I have a clarifier like this, okay, this is the surface, this is the bottom. Yeah. So, in the secondary clarifier, the sludge will settle, right? Okay, the blanket is the surface. Okay, how deep is the blanket from the surface? Of course, we want it to be as deep as possible. Then your water will be very clear. So that's a sludge blanket depth. So what parameter? Okay, now we have this one for liquid sludge. So next is what parameter important to design MBR? It's the same. except that we have a membrane parameter which is flux and aeration rate. What is the flux? Flux is the flow of filtration, and then the aeration rate is the air required to clean the membrane, because we try to clean it with air bubbles. Okay, bubbles. So if things plot on the surface, if I have bubbles, it will score off things from the surface. Okay, and again, well, the calculation I will give you, but these are the important parameters. We have to maintain this parameter, food to microorganism ratio, remember? Okay, how much food per microorganism in MDR, okay? Okay, in MDR we have very low, 0.04. This is 0.16. It's 4 times less food. Yeah. So we put less food, so we can have how to provide less food is by increasing the concentration here. This is the concentration of the biomass. Mixed liquid suspended solid. That's what MLS says. You see here, this is higher. 8 to 12 is 2 to 4. You see here, this is 4 times, and this is 4 times. So 1/4 and then 4 times. So to lower the food is by to increase the volume, the number of the cell biomass. And then for the MDR, we have a longer retention time. This is the SRT, is how long the cell is in the system. Okay, it's a sludge retention time. This is about double to triple. So the consequences is produce less excess sludge. And then the flux. Okay, this is the only for MDR. This is affecting the membrane cost and energy for cleaning. Okay, okay. This is the summary of the calculation. How to explain it? It's a lot of numbers. Basically, it's very simple. Okay, we have a few parameters input here. Capacity is 4,000 cubic meter per day. This is the input, and then we have the inlet BOD around 200, and then this is the settleability of the sludge. Okay. For activated sludge, we target outlet BOD of 20. The concentration of biomass is 3, and then retention time is around 8, and this is the parameter for the MDR. So if you have the file, if you have this file at all, okay, you'll be able to input. For example, the thing that you can input is I put on this color, purple. For example, how if I increase the BOD, what will happen? This is just a process simulation. To increase it to 500, okay, I increase it to 500. You see what happened to this value here. So if I press enter, you see the required volume is higher. Okay, so the same volume, but the volume created is higher. The retention time is higher. Okay, if I reduce it to 100, then you see a lot of change. So at home, if you are a good student, okay, for example, what will happen? What will be the effect of BOD to the excess sludge? Okay, so this is the excess sludge, kilogram per day. Okay, so now I have 100, so it's a 100, then I have 152, so I change this one to 200, so I have 320, 321, and I change this to 300, I have 489, 300, I have 490, let's say I bring it to 400, So I got 659. 659. Let's go while with 700. Okay, 700. It is 1166. This is quite a very nice model for you to do the exercise. And then I'll go to 1000 last. What will happen? And then here is 1672. So, okay, so 1672, and here is 1000. So if you want to see what will be the relationship between BOD and excess sludge, okay, then you can plot this too. I also don't know. So first time I do this. Data. How do we do the plot this? Okay. Here you go there. Oh, it's a linear relationship. There is a linear relationship between inlet BOD and excess sludge. Yeah, of course. Inlet BOD is like the measure of organics. You will convert into the solid. See, then it's trying to make sense of it. And then you can change the what will happen if I change the composition of biomass, if the properties of my microbe also changing. So you can keep doing this one to understand the relationship between parameters. Okay, and then you ask me how to calculate. Okay, I'll provide you with the calculation. What is it? The calculation. Okay, this one. So I'll send it together later on. I take it from a simulation in a book. Okay, this is the calculation process. Okay, so you can, if you are really want to master this one, you can redo, like check the calculation in my sheet. And you will be able to master something that will take 5 to 10 years. And engineers do this one to understand. Okay, to be honest, I prepared this material probably like 5 years ago. Materials. Until that time, I didn't understand. Just because I had to teach, and then at the time I got to teach the wastewater professional. So I cannot get it wrong. So I go to the book, go to the library, and start studying the book. Now after 15 now, so I learned wastewater 2004, and at the time 2000 and okay, after 15 years, then I really understand. Oh, this is what happened. This is what happened to the things. But it's good for you, so you don't have to be like me, learn the hard way. You try to go with this. Okay? And then the same thing, you can do simulation for India. How much membrane area required, what will be the aeration. It's also expensive knowledge. My lecture on this is not all, part of it is available in YouTube. Mostly I got email from people asking me this. Okay, please can you please give the module exercise and the calculation. Yeah, a lot of people from Korea, from US, from Europe. Okay. So please go ahead with the simulation. You have some number of slides. So when you do the simulation, okay, when you run a simulation between the two, then you will be able to see the difference between the two. And these are the samples. The volume, if you treat the same waste, the bioreactor will be about the same. The bioreactor volume. Effluent BOD, of course, MBR is better. Aeration rate, okay, you look here, aeration of the MBR is twice biological. Aeration means lower. Lower means energy. So energy required to operate MBR is way higher than aeration. But then sludge production, see sludge production, this one lead to 90% lower. It's actually not, it's not 90, this is 50, right? Okay, 50% lower. So the cost of handling of sludge is less. So things that you pump for the energy for aeration is compensated with the cost of sludge production. Okay, that is an MBR. Some of the difference, MBR doesn't require qualifier, so you save footprint. If you count the area as well, then it will be also a factor. But in MBR, the minus is that we require the membrane itself and the filtration system. Here we have a trade-off between aeration energy, MBR higher, but then the cost of handling sludge is less, and then actually this is the thing, substantial cost saving for lower cost for the excess sludge. Okay, that's the thing. Can we do it for industry? Yes. I mean, later on when we have time, or maybe in the future. You can go to this website, the mbrsite.com. The website is owned by a Stanford University professor, okay, teaching everywhere in the world, teaching about MBR. Basically what you learn. This guy. It has a website, you can look into all the application of MBRs in the industry. So this is a simulation of how can you compare between the two when treating industry. Okay, when treating industrial waste. What is the very basic difference? Okay, industrial waste normally has high concentration of BOD. Okay, that's the thing. Just a high concentration of BOD. That make it way a bit different. You can run the simulation. In the Excel sheet you have the two. I can send you just after this one. Okay, and then after you run the simulation, you change the number, you see the behavior. Then you will be able to compare basically what will be the difference between conventional system versus MBR when treating industrial waste. You see here, volume will not be affected, effluent BOD always, MBR is better. Here you have aeration rate, and then source production. So more or less, you see these things, okay? Efficiency based on clarifier, it's capex, the minus of MBR is you need to buy the membrane itself. You pump air more, that's energy, and but you produce less sludge, that reduce the cost. Okay, so this is simulation that we run. Okay, upgrading. Okay, upgrading is very simple. So I do simulation, same input, but one in the activated sludge, and one is MBR. Use the cell and then you see, okay, the difference. Okay, I made it handy. That's a work of days of me thinking, and then one day of making the simulation. You know, you will find that you become the most productive when you are under stress, under pressure. Okay, there's a limitation. Yeah, I offered you this one before. Cost is higher. Capex, you buy the membrane, but then you have less area required, so also less capex. Okay. For the energy intensive, mostly for the aeration. Fouling, remember, this is my life. I feed myself, my family because of this problem. Solving this membrane fouling, the fouling is when your filter is clogged and you have to clean it. So even until today, I'm still doing research on this. Okay, with Prof. Yusuf Wibisono. It's the same area of research. A bit complex actually. I didn't touch into the MBR operation. We don't have time. But if you are interested, later on I can send you the video, YouTube video. Other things. This is the summary. I think I have summarized before. I'll quickly skip this one. And then I'll move on to my next topic, which is the nitrogen and phosphorus removal. Before I continue to the next topic, any questions so far? Can you follow me? Not too fast? Okay. Yeah. You know, I always want to come to lecture entertain. That's my thing. And then in fact, if you are noting, it's a good thing, it's a bad thing. I don't used to take notes. Because I will try to remember everything. But, okay, we relax a bit. I don't want you to bombard you with facts. So I moved to Europe for my PhD. And there I was shocked. Because I was like a smart student who never take notes and just pay attention and memorizing information. When I don't understand, I will ask questions. So I make sure to really use the lecture time to master what the it is. So I will come prepared. No, not ever. Then I went to Belgium. I was in the class. Everyone was taking notes. Everyone. Except me. I looked at the lecturer. And the lecturer was like, I didn't take notes. And then come a time when I become the instructor, lab instructor. You know what? We give briefing like this one. No one look at me. But they're busy noting. Oh, nothing, yes. Until last moment. Think about nothing, it's a bit strange. Taking note, but it's good for you. So, I sit in a room with another PhD student, and we have this handbook of membrane technology. I look into the book, and you know, every line is underlined. From the beginning to the end. You know, the English people often call, you have to read from cover to cover, meaning that from the beginning to the end. And she did it all. And then I was like, wow, I got to prank her. So I said, hey, I go to your book and then I look into the book, you underline every line. Why is this? Yeah, because it's important. Well, if everything is important, you don't underline it. Everything is important. Why do you underline? Yeah, that's because they were trained on how to take note. Actually, if you go to the traditional UK in Europe, there is a skill to take a note and then to read things that we don't have here. Okay, now we continue later. So next is that we've been talking about an organics, right? And then we simplify it, okay, by just assuming it's a carbon, nitrogen, everything all in a good proportion. Sometimes you have a wastewater that doesn't really into proportion. Proportion means like you buy a rice in a restaurant, everything with rice, you have the protein, you have the vegetable, all the things. This is just a set food. But sometimes you have to do a la carte. A la carte means you have to pay one by one. So you have the rice and then you have to, okay, I need one chicken, blah, 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 right? So sometimes the a la carte is like, you don't have a set, but you have the a la carte. So you have a lot of nutrients, a lot of nitrogen, a lot of phosphorus in your wastewater. So you cannot treat it like a set. You have to treat it in a special way. So, okay, because why? When these two are abundant, we will have issue with eutrophication, and then it can be contaminated. When nitrate is in our waste, it can be contaminated. So nitrate is quite, the affinity to blood is quite high. So your blood doesn't function. It's poisoning. That is why regulation is quite strict. And actually, nitrogen and phosphorus is expensive commodities. Okay, it's the lifeline of the nation. Wow, I make it less not dramatic. It's true. You know now the problem with our farmer. You are from FTP, right? It's the fertilizer. Fertilizer is basically nitrogen and phosphorus. Well, it's very tricky, right? It's a waste, but at the same time we need it. So that is why we need to, how can we recover it? And instead of instead of assign it as a waste, it's a resource, it's something I want to take back. Okay? Yeah, if you master on this one, you save the nation, you save us, Indonesia. Okay, nitrogen first. Nitrogen available in different forms. Okay, it can be in organics, part of the building block of cells. It can be in the form of ammonical nitrogen, nitrate, and nitrate. And then in order to reduce this one, it has to go through long process. Okay, ammonical nitrogen, nitrate, and then become nitrogen gas. Okay, this is a part here. Okay, in the beginning I give you one chemical reaction. Okay, now we have more reactions. Okay, first it has to oxidize the ammonia. Okay, then it has to oxidize the nitrate. Okay, and this one happened at a very specific condition, particularly this one, long sludge retention time. What does that mean? Is that your volume must be large because it has to stay there very long. Okay, whenever we deal with this one, now I have a volume of quite large. Okay. The next is denitrification. This is when we nitrate, you oxidize into the nitrogen and stabilize it. Okay? In order to do this in a bioreactor, okay, you will need to have more chamber. Why? Because I want to accommodate the set of microorganisms that can do me this and can do me this one. Nitrifying bacteria. The nitrifying bacteria. So this is it happened in our daily life. The only problem is that how could you implement this, put it in your treatment system? Okay? In order to do that, we have a quite complex process. Okay? I'm not very clear, but later on I'll pass to you the slide. We have normally anoxic and aerobic condition. Anoxic is to accommodate the nitrifying bacteria. Sometimes you have the three things: anaerobic, anoxic, aerobic types, and then another time you'll probably need settling and then this lot of recirculation. So that made the process quite complicated. Okay, whenever you have nitrogen. Okay, so next is that what challenges is you need a carbon removal thing. You have a lot of microorganisms. Yeah, this is the analogy. Okay, a lot of microorganisms. Mostly they are carbon sucker. So immediately drop down the CO2, the chemical oxygen. The nitrifying bacteria, it has to survive. They are very slow eating. Okay, imagine in this room, most of us will just boom and then consume. Before these guys finish eating, it's already finished. Now the problem is that how can we design a system so that all of this life in harmony? It's complicated because most of it they really want to consume the food, but there's a small minority of the nitrifying bacteria. I don't want to eat now. Okay, yeah, but it's already finished. Stuffing. So that makes this one is being isolated and dying. That is why you have to do this. You have an anoxic. So you have to limit. So this food crazy microbe, they need oxygen, right? Oh, how can we limit it? Let's limit the oxygen. So that is why you have an anoxic. You have an anoxic, the condition where we have a very low concentration of oxygen. The aim is so that the microbe that like to oxidize the carbon, they don't eat so much. Because if it eats so much, the other one will die. Now you know, right? See, engineers are very smart. If you understand that, it's a logic, right? It's quite logic when I present it this way. But in order for me to understand, up to this point, it takes me years. Yeah, it takes me years. But that's the analogy. So you have different set of microbes that need different conditions. And this is how the engineers do it. And then there are the models to understand this one. The one I showed you before was the simplest one. This one is ASM1, ASM2. I say sampai mati pun saya tak faham. There are a lot of equations, 20 equations. You have to solve it all at once. You have to build your own software to solve this one. So that's the third thing. So the carbon limitation, temperature effect, okay, we need to bring it to the certain temperature. So oxygen control, that's why you have oxic condition, aerobic, anoxic condition, and then you have anaerobic condition. Okay, and then you learned this one last time. And then an NO2 emission, this is also the same. Okay, another one? Huh? Yeah. 5 minutes. Give me 5 minutes. Phosphorus is a bit difficult. Phosphorus is a bit difficult. Most of the phosphorus will be taken, assimilated by the cell. Okay. So it's we remove it through sludge wasting, and then okay, there is probably the two things. We also have this issue. Phosphate accumulating organism. Basically, the way to remove it is by let the microbe to consume it. Okay, you consume that one. But the other one is you have a glycogen accumulating organism. Okay, it doesn't remove phosphorus, but it eats the same thing. In order for this organism to uptake the phosphorus, you need to have volatile fatty acid concentration in your system. But okay, we have two things. One we wanted, another one we don't want. But this one is more very serious. It's really like crazy of sucking these things. So there are two things that we need to optimize in order to remove the phosphorus. Another thing is that we need to change the condition, some pH, temperature, and this one, rich carbon sources. Okay, there's other things. I don't think I have enough time to discuss. It's called anamox, anaerobic ammonium oxidation. So the standard way of treating nitrogen is you go oxidizing, ammonia oxidation, and nitrification, denitrification. So the 3 steps. This one is like 1 step. Okay, this is 1 step. You see here ammonical nitrogen directly to become nitrogen. Okay. So it's different condition, different set of parameters. You see here there's a direct way of converting ammonical nitrogen and nitrate into the nitrogen. So it doesn't have to go through all of the processes. So it's more efficient, in fact. More efficient, but we have to slow growing bacteria. So you have the slow growing bacteria, so the solution should be the trickling filter. We use trickling filter, biofilm, and so on. So if we manage, I think I have last few slides. If you manage the nutrients well, we would be the protector of our mother nature, the environment. so we can prevent the eutrophication and so on. So why eutrophication is damaging? So you have a lot of this algal bloom, right? Algae will grow on the surface because it's require light to grow. Okay, so basically it blocked the penetration of the sunlight into the water bodies. Okay, and then the plankton will die because there is no photosynthesis. Fish will die because it eats plankton. Okay, then when fish dies, and then smelly anaerobic condition. Okay, it's really polluting the environment. So it's like a complicated disease, you know. When getting old, you can start with your sugar problem, goes to this problem, goes to that problem. Yeah, that's it. Although it's just an application, but it will lead you to bigger problem. Okay. And then we can conserve the resources and then build infrastructure. I want to close before I conclude. This is quite important. Why treating our water is of a priority. Okay. The book from the Avicenna, right? So they have this as a book, still become one of the main reference of the books. From that book, it says prevention is better than treating. Okay, so if you can prevent all of this eutrophication, all of that introduction of the pollutant to the water body, that is way cheaper than treating the whole river. Okay, otherwise you're treating the whole river, it's kind of impossible. Okay, okay. So these are 4 key takeaways. Number 1 is 4 topics. Design with the end in mind. Okay, what do you want actually? Okay, like for example, I want to remove the organics, mainly carbon. I want to remove mainly the nutrients, nitrogen, phosphorus, and so on. Got to think, what do you want? And then, in designing, how could we achieve what we want? Think, and then MBRs, I introduced one of the options that is emerging. I think now it's already leading for the new water wastewater treatment plant. So it's your part. I mean, mine is actually sludge. Your future is more on MBRs. Then biological nutrient is essential to protect ecosystem. And in the end, I refer back to this one, is that maybe we got to rethink back, because now people start to think why we keep blaming the waste. Can we do something out of it through what we call as a resource recovery? Okay, water, wastewater. Majority of water is resources, our lifeline. The very small part that make it become waste. How can we do things? So instead of managing it as something to throw away, okay, we manage it for something to take back. Okay, that's the thing for the resource recovery. With that, I close my lecture. Thank you very much for your kind attention.
Okay, thank you very much for the insightful knowledge you shared, Dr. Roil. And yeah, it's reminded me maybe 15-20 years ago to have a lecture from a professor and some experts from other countries about Rajampo and many things. And I think we have only 10 minutes. Any question? Yeah, please. Yeah, please.
So my name is Lana. I'm an assistant for sludge disposal. So you say that we can burn the sludge, or we can dispose the sludge, or use it as fertilizer. what kind of slots that we can burn, or we can just ask for that?
Okay. So in the end, you have three streams. You go in the wastewater, and then you have the treated water, and you have the waste sludge. Waste sludge is basically a sludge with high concentration. So what we do normally is that thing we filter using a filter press, and it's become filter cake. Okay, that cake is really up to you. What are you going to do with it? Okay. The easiest way is that you send it to landfill. But I know we have to look into the regulation whether we can throw the sludge into landfill. Okay, throw landfill. Or what you do is a sludge. You can burn it. Or some will have an anaerobic digestion. Put it into anaerobic digestion, and then it will be again anaerobically oxidized. It's produced biogas, CO2 and methane. Those are the three options for the sludge. Fertilizer is an option, but you need to stabilize it first. Fertilizer. The fertilizer is actually what I refer to is the nutrients. Okay, you have wastewater containing a high nitrogen, for example. That maybe should be considered as fertilizer. Okay, good.
Any other question? Maybe from this side? Okay, two questions. Maybe the first one. You can introduce.
My name is Nia. I want to ask, like, the MBR use microorganisms to degrade organic compounds, right? So what if the wastewater from previous processing step still contains like toxic compound that cannot degrade by microorganisms? Can MBR be adjusted to untuk pengolahan si limbah yang masih
Yeah.
okay.
So, okay, very good questions. Well, it is really toxic. Then it's toxic. So the biological is not solution. You can do the chemical oxidation, Fenton oxidation, master of Fenton oxidation. You can do chemical degradation. Okay, but let's say, but this is expensive. Okay? Creating chemicals radical is quite expensive. The bio is the cheapest way and the most natural way of doing it. So what we do is normally, if it's still possible to grow microbe into it, then we'll go for it. The way to do it is a step called acclimatization. So we train the microbe slowly to consume the things. Or if you expose a group of microorganisms to that substances, polluting not so toxic pollutants, in the end, some of them might be able to degrade it. So this is what we call as acclimatization. So in the end, only this will survive. And it's become, the composition of the cell become unique, that handle that kind of waste. Okay, that's the thing. Okay, that's called acclimatization process. Okay, so the option is maybe the biology is an option. You have another option, chemical oxidation. In case it is still possible to do biology, we need to do acclimatization process, and that will normally take some time. And it's growing. It's growing fast. Okay, this is the thing. How to say? What is the dominating species on the earth? Human being. Why? Because we know how to consume resources. The same thing. So at the end, there will be one species or few species that really can strive under that environment, that will do the job. Okay, but normally toxic, unless you do it in a very specific chemical, it's already regulated, so it won't let to the water body. Normally it's very, very regulated. That's what we call a scheduled waste that has to be handled with care. Even you cannot easily buy toxic chemicals. Okay, yeah. So yeah, that's a good question.
Okay, the second.
Okay. My name is Naila. It's actually, my question is different than your explanation before that how much the percentage of the MBR can we use with especially toxic wastewater like pharmaceutical or maybe waste from hospital, because we know that the MBR process does not require disinfection. So, like, how much the percentage of?
Okay. Okay. Number one is disinfections at the end. Okay. At the end means that we don't want to our discharge to be polluted by living microorganisms. Okay. If a wastewater contains pharmaceuticals, for example, this is a big issue. Why? Because the microbe will only, because it comes with others, right? So I have organics, range of organics, easily digestible and then hardly digestible. So what happens is the microorganism will only consume the easily digestible, and then this guy will not be consumed. So it will go through the discharge. Okay. Can MBR do that? It tastes better than conventional because MBR allow growing different species of microorganisms. Maybe in the long run, when the population of this particular microorganism is high, it will be able to somehow reduce it. But normally, pharmaceuticals, hospital waste are in a very low concentration. Very low concentration. And that is the current issue in the environment. There are persistent chemicals that bypass all of the treatment because the microbe will not eat it. Imagine an antibiotic. You know what antibiotic is? It's a thing to kill microbe. How do you think the microbe will consume that? It's killing. Okay, so it will, because the concentration is low, it doesn't damage the microorganism. It's still going towards the body. So I'm teaching a course in pharmacy department, but not UB, but in another university. We're talking about this one, accumulation of persistent chemicals, including the pharmaceuticals in our water body. The thing is, it's very low concentration. So UV is what? So how can you treat, for example, you are try to pinpoint UV got 100,000 students, let's say in campus. There are only 3 of them here. Okay, how are you going to find out this guy out of the 100,000? To treat that one is very hard. Yet that is why regulation is getting stringent and stringent, right? Lower the parameter. So at one point when you know what is pollution? Pollution definition is that when there is a thing that exceeds the threshold concentration. So at one point it will exceed the threshold concentration and people will ask, why are we noticing it too late? Now I'm telling you, we are polluting our environment. Very good. Okay.
Thank you for the answer. Any other questions for the last question?
Pointing test it.
Thank you very much, Prof, for the lecture today. Prof, we would like to ask related to applications later, but this is from water pressure. This one. Well, today I'm studying this my dissertation related to hydrophobic membranes in the science. I'm going to read some first how to imagine forms of the membrane, especially for selected, how to select the polymer and green solvents and the differentiation of applications like electrospin and etc. So actually this is this is my class for supervisor, Prof. Please give me some analysis or interesting topic related to how to aging additive or tubular besides hydrophobic membrane.
Hydrophobic.
Hydrophobic membrane. Then will be applied to related membrane distillation. It will be applied in membrane distillation.
Membrane distillation.
Yes, to treat and practice MC water. To
Oh, yeah.
prevent water. This is
So hydrophobicity is derived from many aspects. Most of it is from the structure, surface structure. Your material must be hydrophobic one thing, but the hydrophobic material is just you just reach some point. It's no hydrophobicity anymore. Okay, so in order to increase the hydrophobicity, actually we play with the structure. It has to be a mixture of micro and nano structure. So you will have the what's called the effect. It's like the daun talas. Yeah, daun talas we have the rambut itu. That's a nano scale, and then you have also the curvature of the surface. So it has to be in between, so that you can entrap that on the surface. That can impose hydrophobicity. Adding stuff will not help. It will not significantly help unless your base polymer is hydrophilic. Most polymer, they are hydrophobic. So actually, every polymer, every membrane is actually hydrophobic. So, but we want to make it extremely hydrophobic. So you need to play with the structure, the surface structure. You can coat hydrophobic. How can you create the things? Nano scale and micro scale roughness on the surface. Less to do with editing. Okay. Yeah, it's quite challenging. Okay, any question? Other questions? Okay, I have another.
Yeah. Okay, I think that's the last question. And one more time, thank you very much for the lecture from Associate Professor Muhammad Roil. And I think this is the end of today's learning program. And on behalf of the committee, I will close today's session. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Roil, for the new insight. Before moving on into today's last session, we would like to have a group photo together with our guest speaker, lecturer, and all participants. We kindly ask everyone to come forward for the documentation session and smile for the photo.
You sit down. Sit there.
Satu, dua, tiga. Satu, dua, tiga. Satu, dua. Sekali lagi, satu, dua, tiga.
Okay.
As we come to the end of this event, we would like to express our deepest gratitude to Dr. Roil for taking the time to be with us today. We have prepared a little gift for you, Dr. Roil, and Mr. Angga, I would invite you to do the gift handover. Once again, thank you, Dr. Roil, and we would also like to say thank you to Mr. Lugur for leading the guest lecture this morning. That concludes our guest lecture today. Thank you to our distinguished speaker for the valuable knowledge, and thank you to all participants for your active engagement. As Master of Ceremonies, I apologize for any wrong words or deeds. We hope today's session was beneficial and inspiring. Stay healthy and stay inspired for a sustainable future. See you at our next event. Have